In this section, we are going to talk about rational functions. So a rational function, notice that it has the word ratio in it. So there's going to be a ratio of two functions. So it's going to be in the form p of x over d of x, where both of these are polynomials and d of x cannot be equal to 0. The domain of v of x is all real numbers except the zeros of the d function. And we've talked about that before when we talked about implied domains. Okay, when the denominator is equal to 0, that gives us our vertical asymptotes. So if we're given some rational function and it's written in its simplest form, vertical asymptotes will occur at the real zeros of d. So back in chapter 2, we talked about toolbox functions. We're going to add two more toolbox functions to our set. So here we've got what they call the reciprocal function, which is y equals 1 over x. And you can see that they created some xy points and then plotted those points. So this right here becomes our function of y equals 1 over x. Another function that is going to be one of our toolbox functions is y equals 1 over x squared. Okay, and so they have the graph up here. Okay, so again, they created an xy table, plotted a handful of these points, and you can see that we then end up with this function right here. Okay, this function is sometimes called the volcano function because it looks like a volcano. So this is y equals 1 over x squared. The thing about these toolbox functions is that they shift or they have a transformation just like all our other toolbox functions. So for example, here we have f of x equals 1 over x plus 1. So that's the first function that I showed you. Pull it up here. So this one right here, notice where the function exists. And so this function down here has the same exact form, but notice that the entire function is shifted up 1 unit. And that's because of this plus 1 at the end. Okay, here's our volcano function. Our function is written as 1 over x squared, so that means that's our volcano function, minus 2, which means it's going to be shifted down 2 units. Okay, I'm going to show you one more transformation. So this function right here, notice that it has the same form as 1 over x, and then it's shifted, and you can see these dashed lines help us show how it shifted from that origin. So this graph right here, it shifted 2 units to the right and then down 1 unit. And you can see that from our function. So we have 1 over x, so that tells me that it's the first function I showed you. When we have x minus 2, that's telling us how we shift left and right. So remember, it's opposite of our shift. So since it says negative 2, that means we're going to shift 2 to the right. And then this negative 1 tells me I'm going to shift down 1 unit. Okay, so that's two more toolbox functions. What I want to look at next, actually let's keep this here. Okay, so here we've got another function. I'm going to try to zoom out a little bit. Hold on one second. All right. So what I want to do with this function right here is I want to look at the end behaviors of this function. Okay, so notice that this function up here, it's negative 3 over the quantity x plus 4. Okay, well this is the toolbox function of 1 over x. This negative tells me it's reflected over the y-axis. The 3 just tells us how it's stretched. And then this 4, since it's a positive 4, tells me it's going to be shifted to the left 4 units. Okay, so this right here is a transformation. Okay, and so what I want to talk about is the end behavior. So let's start with this end behavior right here. So as this function continues, notice there's an arrow there. So as that function continues going in this direction, we want to know how that arrow behaves, or how that function behaves. Okay, so I'm going to call this 1, so that way down here I can put a 1 and talk about the end behavior. So as we follow this function out, notice that the x values are getting smaller and smaller. So it goes -7, -8, -9, -10. Those values are getting smaller. So we're going to say, as x approaches -infinity, the y values, notice that as we follow this function, these y values are getting smaller and smaller. So we're going to say f of x goes to 0, and then we put a little plus sign to say that it's approaching 0 from above. Okay, the second one, let's go ahead and call this one over here end behavior 2. It doesn't matter what we number them, I just want to be able to write it down here. So this end behavior, notice as we follow this function, the x values are going to get larger and larger. So that means that as x approaches infinity, f of x is going to approach, meaning we're going to look at the y value. So as this function goes out, the y values are getting closer and closer to 0, but notice they're now approaching from below. So we're going to say 0, and then with a little negative sign up here to say it's from below. Okay, now we can talk about this end behavior. So on rational functions, we'll have 4 end behaviors. So the third end behavior, okay, so as I'm looking at this function, as I'm following or as I'm tracing this function, the x values are getting closer and closer to -4. Notice they're approaching from the left side. So down here we're going to say x approaches -4 from the left side. So that's what that notation means. So it's approaching -4 from the left. Okay, and then we want to see as x is approaching -4 from the left, the y values, you can see as we trace this function, the y values are getting larger and larger. So that means that they're going to infinity. Okay, and then the fourth end behavior is this end behavior right here. Okay, so as I'm tracing this function, these x values are getting closer and closer to -4, and they're approaching from the right. So we're going to write that as x approaches -4 from the right. Then f of x, meaning the outputs, as we follow this function, the y values are getting smaller and smaller. They're getting more negative. So then we say this is approaching -infinity. Okay, something I can do to help you see that if you're not quite sure where those numbers are coming from. And I've done this in the past, and sometimes it helps students, sometimes it doesn't. But hopefully it'll help you. What I'm going to do is I just have this transparency, and you can see that I've got a grid on it. And so what I'm going to do with this middle part, or this center, is I'm going to follow the function with that center. And then I'm going to show this line right here. Okay, good. So that's pink. We'll do the other one purple. Okay, and what I'm going to do is I'm going to trace the function so you can see what's happening with our outputs. Okay, so let's see. Actually, let me do pink all the way across. That'll make it easier. Alright, so as I follow the function, so I'm going to look at end behavior 1 here. Okay, so as So again, that origin, I'm just going to trace along my function. And so as we do this, I'm going to do it a handful of times. So as I follow the function out, I want you to pay attention to what's happening to the purple, which is the x value, and then pay attention to the pink, which is our y value. Okay, so as I trace this function, as I'm going out towards end behavior 1, you can see that this purple is tracing along smaller and smaller x values. Okay, so that's why x down here goes to negative infinity. Okay, now we're going to pay attention to the pink over here. So this is our y value. So as this is following my function, you can see that the pink values are getting smaller and smaller, and they approach that x-axis, meaning we're approaching 0. And so that's why I said this right here. So the y values are approaching 0 from above. Okay, I'm going to look at end behavior 2. So we wrote that right here, that as x goes to infinity, f of x goes to 0 from below. Okay, so again, this origin, I'm going to have it following my function. Okay, we're going to look at this purple, and we're going to see how that maps on our x values. So as I follow the function, you can see that this purple line is following larger and larger x values. Okay, so that's why I said x goes to infinity. Let's go ahead and trace that again, and now we're going to watch this pink line right here. Okay, so as I trace along my function, actually let's start way down here, make it a little easier to see. Okay, so watch this pink line. Notice that pink is going to smaller and smaller y values. Okay, and eventually we get really close to that 0, and we're approaching from below. Okay, let's talk about end behavior 3. So we said that as x approaches negative 4 from the left, f of x goes to infinity. Okay, so I'm going to take this purple right here, we're going to follow it along the function, and you can see that as I trace the function and I go out to end behavior number 3, you can see that these x values get closer and closer to 4. Okay, so I'm just following with that function. So it gets closer and closer to negative 4, and it approaches from the left. Okay, and so I'm going to trace it one more time. Now we're going to watch the pink, and we're going to see what happens to the y values. So as I trace the function, you can see that the pink is touching larger and larger y values. So that's why we said f of x goes to infinity. Okay, and I'll do it one more time with this very last one. Okay, so as I'm tracing this function towards end behavior number 4, you can see that the purple is tracing along this x-axis right here, and it's getting closer and closer to negative 4. Okay, and it's approaching negative 4 from the right side. Okay, and as I trace it again, we can look at the pink values, and you can see that the pink values are becoming smaller and smaller as I trace down that function. So that's why we have x goes to negative 4 from the right side, and then f of x goes to negative infinity. Okay, let's look at the end behavior of another function. So here, again, we're given our graph. Notice that the parent function is 1 over, we have x minus 3 quantity squared, which means that our parent function is the 1 over squared. So this is our volcano function, and notice you can see that modeled here. This negative 3 tells me it's going to shift to the right 3 units. This negative 5 tells me it's going to shift, it's going to shift down 5 units. And you can see that on the graph. This is where the origin was. It shifted to the right 3 units, and then it shifted down 5 units. Okay, we're going to again look at the end behavior of these 4 points on our function. So I'm going to call this 1, 2, I'm going to call this 3, and 4. The numbering of those don't matter. We can call them whatever we want. It just helps with my notation. So if I write 1 down here, I know that this, what I write, is going to be the end behavior for this point. All right. So as we follow the function, so I'm going to trace my finger, you can see that the x values are going to get smaller and smaller as I trace this function. So then we say x goes to negative infinity. The output, so as I follow this, you can see that the outputs become smaller and smaller, and then it approaches this negative 5. So it approaches negative 5 from above. So I'll say that one more time. So as I follow this function out, you can see that as I come down, these y values get smaller and smaller, and it leads up to where it approaches negative 5 from above. Okay, looking at end behavior number 2. So as I follow this function with my finger, we want to look at what's happening with the x values. So as I follow it, you can see that the x values are getting larger and larger. So that means as x goes to positive infinity, we want to look at what's happening to the y values. So as I trace this, you can see that these y values become smaller and smaller, and it approaches that negative 5. Okay, and again, it's approaching negative 5 from above. Okay, the third end behavior. So as I trace this function towards number 3, you can see that the x values gets larger and larger until it reaches that 3. So as I come up, my finger was following all these x values until we reach 3. So x is going to approach 3 from the left. Okay, so be careful of that notation. When we have this power up here, that's just telling us which direction. So if it's negative, it means it's coming from the left or below. If it's a positive exponent, that means that it's coming from the right or it's coming from above. Okay, so we say x approaches 3 from the left, then f of x, you can see that as I trace it with my finger, the y values are getting larger and larger. So this approaches positive infinity. Okay, and then end behavior number 4. So as I follow this function, you can see that as I follow it, the x values get closer and closer to that 3. And we're approaching the 3 from the right-hand side. Okay, and then the outputs, as I trace my finger, those outputs get larger and larger. So that means that f of x is going to approach infinity. Okay, so those are the end behaviors for these two graphs. Okay, the next thing I want to talk about is being able to graph rational functions. Okay, so these topics right here are all in your book. They're highlighted in those boxes. So I already mentioned the vertical asymptote. So the vertical asymptote occurs wherever this denominator is equal to 0. It means that the function doesn't exist at that point. The horizontal asymptote, okay, so right here it tells you exactly what can happen. There's 3 different options. So if we're given a rational function and it's in lowest terms, what we can do is we can let the leading term of p be a of x raised to the nth power, and then the leading term of the denominator we're going to call b x raised to the mth power. Okay, so again it must be in reduced form, and then these are the leading terms in both the numerator and the denominator. Okay, well if n is less than n, meaning that this power is higher, I'm sorry, n is less than m, meaning that this power is smaller than this power right here, then there's a horizontal asymptote at y equals 0. Okay, if n equals m, then there's a horizontal asymptote at just a over b. And then if n is greater than m, meaning this n has a higher power than this exponent down here, then the graph has no horizontal asymptote. Okay, and then these are the guidelines for graphing rational functions. Okay, and I'm going to go ahead and follow them. So we're going to find the y-intercept, we're going to find the vertical asymptote, we're going to find the x-intercept, we're going to locate the horizontal asymptote if there is any. We're going to determine if the graph will cross the horizontal asymptote. If need be, we're going to compute mid-interval points, and then we're going to plot all of that information to graph our function. Okay, so here we have our function. We're going to graph -4 all over -5x minus 12. Okay, so as we graph this rational function, I'm going to follow these guidelines right here. And I'm going to go ahead and number them just like they have on here. Okay, so our first step is to find the y-intercept. Okay, so I'm going to label this 1 since it's our first step. And truly the order of these steps, it doesn't matter. I'm just going to follow the guidelines that they gave. Okay, so we want to find the y-intercept. To do that, we're going to let x equal 0. So this becomes -4 over -5 times 0 minus 12, which gives us -4 in the numerator and a -12 in the denominator. That reduces to 1/3. So this right here is our y-intercept. The second step is to find vertical asymptotes. So I abbreviate that VA for vertical asymptotes. Okay, in order to find the vertical asymptote, we're going to set the denominator equal to 0. Okay, because remember we talked about that's where the domain doesn't exist, so that's where our vertical asymptotes occur. So we've got -5x minus 12 equal to 0. To solve for this, we're going to add 12 to both sides, and then we divide both sides by -5. So we get x equals 12 divided by -5, which we can write that as a decimal of -2.4. Okay, our third step is to find the x-intercepts. To do that, we're going to let y equal 0. So this becomes -4 over -5x minus 12. Set that equal to 0. Okay, in order to solve, we're going to multiply both sides by this denominator. Okay, when we do that, those cancel, leaving us with -4. Well, 0 times any term is equal to 0. Notice that this right here is a contradiction. Therefore, so that little symbol, the 3 dots, means therefore there is no x-intercept. Okay, the fourth step is to locate the horizontal asymptote. So we're going to find the horizontal asymptote. I'm going to bring this back up. So this right here tells us exactly what our horizontal asymptote is going to be. First, we need to find the leading terms of both the numerator and the denominator. In this case, the leading term in the numerator is just -4. If we want, we can write that as x to the 0 power. Okay, and then in our denominator, our leading term is just the x value at the highest power, which in this case it's 1. So our leading term is -5x. Okay, well when there's no number as the exponent, we know it to be 1. Okay, so looking at this right here, the exponent in the denominator was 1, the exponent in the numerator was 0. Okay, so that means that m was greater than n. So our denominator exponent was greater than our numerator exponent. Or we could say that the numerator exponent was less than our denominator exponent. When that happens, that means that we have a horizontal asymptote at y equals 0, also known as the x-axis. Okay, so that means that the horizontal asymptote is at y equal to 0. Okay, and I'm going to put a little note on here to see chart. Okay, so that's where we got that information from. Okay, the fifth step is to determine if the graph will cross the horizontal asymptote. Okay, what that means is we want to know that when we have this graph, we want to know if it crosses this horizontal asymptote. Well, since it's at 0, that means we want to know, does the output equal the 0? Okay, so what we're going to do is we're going to take our equation, negative 4 over negative 5x minus 12, and we're going to set it equal to our horizontal asymptote. Okay, so I'll put that in words. So we're going to set the function equal to the horizontal asymptote. Okay, and then what we're going to do is we're going to solve this equation. So we're going to multiply both sides by negative 5x minus 12. Okay, those reduce, leaving us with negative 4 equals 0 times this expression. Okay, well notice that we did that before, and it just is, the reason why it ended up looking like we did it twice is because our horizontal asymptote happened to be 0. Okay, if this was a different number, which you'll see in another example, this situation doesn't necessarily repeat step number 3. It just does when our horizontal asymptote is equal to 0. Okay, here we have a contradiction, which means that our function f of x does not cross our horizontal asymptote. Okay, so most students remember from high school that when we have a vertical asymptote, the function can never cross it. And that's true. But functions can cross the horizontal asymptote. That's why we need to do step number 5. We need to check that. Okay, number 6 says, if needed, compute mid-interval points. And so we'll see if we need to do that, okay, after we start graphing all of this information. Okay, so now what we're going to do is we're going to plot all of this information. So the first thing, it says find the y-intercept. Okay, so here's the y-intercept. We know that it crosses at 1/3. So I'm going to go ahead and put a dot there. Next, we found our vertical asymptote at negative 2.4. So here's negative 2, and it's approximately right here. Okay, so this is our vertical asymptote. Okay, next we found that we did not have any x-intercepts, so we don't need to plot any points there. We have a horizontal asymptote at y equals 0. Okay, so I'm going to go ahead and plot that. Okay, and I'm going to put an HA over here. It's a horizontal asymptote. Okay, and then we know from step number 5 that we did not cross our horizontal asymptote. Okay, well, something to point out that I didn't mention earlier, you can see that our function always approaches these asymptotes. It's like they're a magnet to our function. So as this function is going, it's drawn towards this asymptote. Same thing down here. This function is drawn towards the asymptote. Okay, so if we've got this point right here, that means that our function is going to do something like this. Okay, so I know it goes to this point, and then it has to be drawn, or it's magnetized towards those asymptotes. Okay, because our toolbox function, notice that there's just one x in the denominator, that means that this toolbox function is 1 over x. And so if we look at that toolbox function, remember one side was in one quadrant and then the other side was over in this quadrant here. Okay, so there is our function. If you aren't convinced of that, you can plot some points. So like, for example, I can take this -5, I can plug it into my equation and find the corresponding output. Okay, and then we can do that with any of these. So I can take -10, plug it into the function, and find where my corresponding output is. Okay, what we're doing here is we're just drawing a rough sketch of the graph. We don't need to know every single point and where it's exactly located. We just want to get a rough idea of what this graph looks like. Okay, let's go ahead and do one more for practice. Okay, so here we've got -3x plus 3 all over 4x plus 10. Okay, so we're going to again follow our same steps that we did on the previous problem. The first thing is we're going to find the y-intercept. So we're going to let x equal 0. So this becomes -3 times 0 plus 3 all over 4 times 0 plus 10, which that reduces to 3/10. So this right here is our y-intercept. Second step is to find the vertical asymptote. To find the vertical asymptote, we set our denominator equal to 0. So that means that 4x plus 10 is going to be set equal to 0. Solving for this, we're going to add 10 to both sides. So we get 4x equals 10. And then now divide both sides by 4. Gives us x equals 10/4. Or we can write that as, I'm sorry, that should be a -10 right there, because I should subtract 10 from both sides. Okay, so that gives me a -2.5. The third step is to find the x-intercept. So that means we're going to let y equal 0. So that gives me -3x plus 3 over 4x plus 10. Set it equal to 0. To solve this equation, we multiply both sides by 4x plus 10, leaving us with -3x plus 3 equal to 0 times any expression is still going to be 0. Okay, so from here we want to solve for x. So I'm going to subtract 3 from both sides. So we get -3x equals -3. And then dividing both sides by -3 gives me that x equals a +1. Okay, the fourth step is that we want to find the horizontal asymptote. So in order to do this, we want to look at our leading term in both the numerator and the denominator. So the leading term in the numerator is the one with the highest exponent. Turns out it's -3x. And then in our denominator, the leading term is 4x. So we get -3x over 4x. Okay, now I'm going to refer to my chart. Okay, so notice that, oops, let's go back to that real quick. So notice that the exponents are identical to each other. So the numerator has an exponent of 1, the denominator has an exponent of 1. Okay, so here when the exponents are the same, that gives us situation number 2. So if n is equal to m, then we have a horizontal asymptote at the coefficients of a over b. So in this case, we're going to have a horizontal asymptote at -3 over 4. So I'm going to say the horizontal asymptote is y equals -3 over 4. Okay, the fifth step is to determine if f of x crosses the horizontal asymptote. Okay, so I'm going to take this -3x plus 3 all over 4x plus 10, and we set it equal to the horizontal asymptote. Because I want to know, does this have an output that's equal to this right here? So we get -3 over 4. And now we want to solve this expression. So the best way to explain is to do that cross multiplication. So I'm going to take negative 3x plus 3, multiply it by 4, equal to 4x plus 10, multiply it by negative 3. Okay, I'm running out of room, so I'm going to go ahead and bring it up here. Okay, so I'm going to distribute that 4, so we get negative 12x plus 12 equals, and I'm also going to distribute that negative 3, so we get negative 12x minus 30. Okay, I'm going to add 12 to both sides, add 12x to both sides. So we get 12 equals, that reduces to 0, this reduces to 0, so we get 12 equals a negative 30. Well, that is a contradiction, which means, or thus, f of x doesn't cross the horizontal asymptote. Okay, so now let's go ahead and graph this. So we know our y-intercept was 3/10, so that's approximately right there. We know we have a vertical asymptote at negative 2.5, so that's right here. So this right here is our vertical asymptote. This time we have an x-intercept of 1. So here's the x-axis. Here's our x-intercept. Okay, we have a horizontal asymptote at negative 3/4. So that's approximately right here. Okay, and so again, let's see actually, and then the last thing is that we know that it doesn't cross the horizontal asymptote. Okay, so again, this function is, we've got 2 points, and it's going to be magnetized towards those the asymptotes, either the horizontal asymptote or the vertical asymptote. Okay, over here what we can do is we can plot some points just to see where this function exists. So let's go ahead and plot, it doesn't matter, let's do, trying to think if there's any good numbers. Let's go ahead and just choose negative 5. Okay, so we're going to do f of negative 5 equals negative 3 times negative 5 plus 3 all over 4 times negative 5 plus 10. So in the numerator, we have a positive 15 plus 3 gives me a positive 18 over, this gives me a negative 20 plus 10 gives me a negative 10, which means that that reduces to negative 9/5, or we can say negative 1.8. Okay, so that means that at negative 5, the output is at negative 1.8. Okay, so that means our point's down here, which means that our entire function must be right through here. Okay, again, it's drawn towards those asymptotes, and we know it doesn't cross this, so that's why we know that the function must stay on this side of our asymptotes. Okay, one thing to just quickly point out, because it's rare that we'll see, especially in this class, that the function crosses the horizontal asymptote, but it does happen. And so when it does occur, so let's say we have our horizontal right here, and let's say we have a vertical asymptote right here. So our function may look something like this, where again it's attracted towards our asymptotes, and then this right here, it could bounce below the horizontal asymptote, but then it comes back up and it becomes attracted again towards that horizontal asymptote. So notice that it can cross this horizontal line and then approach it from the other side. Okay, so it does happen, and that's why we always need to check for it. Alright, so make sure when you're graphing rational functions that you just follow those steps as the guidelines. That is it for this section.